Welcome back to this week's episode of Chapter 6 in Calculus. This week, we'll be looking at volumes of revolution using washers. If you remember the last time, we were doing volumes of revolution using disks. This is simply the next step in the process. It gets more difficult volumes of revolution, ones that aren't solid all the way through. And so, to look at this, the first thing we're going to look at is just the area of a washer. What do I mean when I say washer? That's not like a washer as in a washing machine. It's a washer as in nuts and bolts and washers. It's a circle with a circle cut out of the inside. Now, if we're finding the area of this, which we have done ever since geometry, maybe even before, we know that the area of a circle is pi r squared. So we're going to have the area of the big circle. The radius is r2, so that's going to be pi times r2 squared minus the area of the inside circle, pi times r1 squared. Now when we're doing this, this is the formula is going to be, we'll multiply on a dy or dx, depending on which way we're cutting it, but this is the formula. Notice the pi's are in both places. We can factor the pi out. So we'll end up with pi times r2 squared minus r1 squared. And then we're going to end up finding the antiderivative, and we'll get a dx on the end or dy on the end, and these guys will have to be written as x or y, just like in the disk method, just like what we were just doing. It's just we have two of them. Now, this looks kind of reminiscent of section 2 as well, because we had the big one minus the little one squared. The big difference here is it's not the big one minus the little one squared. It's the big one squared minus the little one squared. Notice the square, they're on the inside. It's not out here like it was in section 2, because in section 2, we were just taking this distance and doing something with it. Now, we have to take the full area minus the other full area, and that does make a difference. So, let's look at what some of these volumes are when we rotate. First, let's rotate around the x-axis. So we're going to have a shape. The shape is this guy that's y equals x squared, y equals root x. Rotate around the x-axis, so it goes that way to form this shape over here on the right. Now, sometimes it's nice to have both the pictures, but I would always start out with a graph, just the two-dimensional graph, so that you can see what your radii are. Our radii, we're going to have the big radius goes from the x-axis up to that upper function. And then the little radius goes from the x-axis to the lower function. Now when I'm setting this up as an equation, we're going to have the volume equals pi times the antiderivative. We'll get the bounds here in a second, but we're going to have the big radius squared minus the little radius squared. These are y distances, right, because they're vertical distances. So this is going to be y squared minus the little one, y squared. And then we revolve around a horizontal. The width of each of these things is an x distance, so we have dx. Just like last time, we're either going to have y squared dx or x squared dy. It's just now we have y squared minus y squared dx. Now, on the previous slide, we had r1, r2. This is y1 and y2, but instead of using the subscript 1 and 2, I just use colors. We have the red y and we have the blue y. Sometimes the subscript, that extra number, just seems to get in the way. So we have the red y and the blue y. Now, like we did with the disks, we need to plug in for x's in there. So we have the red one is the upper one, which is y equals root x. So this will be root x squared minus, and then the blue one is y equals x squared. So that'll be x squared squared. Then we'll get a dx. We'll have the pi times the integral. Oh, and our bounds. Where are our x's going? In a lot of these, you're going to have to figure out where they intersect. Sometimes they'll tell you, but you might have to figure out where they intersect. In this case, with our graph, it's fairly obvious. So, hey, look, it looks like they intersect at 0, 0, and 1, 1. Let's plug them in. Is 0 squared equal to 0? Yes. Is 0 equal to root 0? Yes. Same thing with 1. Yes. We didn't have to set them equal to each other. We could figure out that they intersect at 0 and 1. But if you need to, set them equal to each other. So our bounds were going from 0 to 1 and 0 to 1. So we can simplify these. We'll have the volume equals pi times the antiderivative from 0 to 1. Square root of x squared is just x minus x to the fourth. Not because 2 squared is 4, but when we have a power, we multiply 2 times 2 equals 4. dx. Now we're ready to find the antiderivatives. So we can come up here, we'll have pi, x becomes x squared, so we have 1/2 x squared minus 1/5 x to the fifth from 0 to 1. So we're going to plug in 1. So that'll be 1/2 times 1 minus 1/5 times 1 minus plug in 0. In both these cases, it is 0. Be careful when we have like e to the x, because e to the 0 equals 1. It does not equal 0. So 1/2 minus 1/5, this would be a 5/10 minus 2/10 is 3/10 times pi, gives us 3 pi over 10, which is about equal to 0.9425 or so. So we have the exact answer, and we have the approximate, which is the decimal. I recommend, especially for ones like this where you can see it's like, oh, hey, we can find the antiderivative of that. It's not going to be one of the crazy hard ones. Do it by hand. Practice doing it by hand. Sometimes on the AP test, which is one of the things we're practicing for, that's what our final is going to look like. This is a no calculator problem, and you have to do it by hand. Sometimes it is a calculator problem, and you'd be expected just to plug it into your calculator. In that case, it's probably going to be a bit harder. But at the very least, if it's sometimes, or if it is a calculator problem, you have to set it up first, and then you can get to your answer. So you can go from this step or this step straight to this step. Sometimes when it's a no calculator problem, especially if it is a harder one, this will be part C. You've already found antiderivatives in the problem. It might just have you set it up. And we'll see a lot of that coming up in about a month or so. We'll have lots of practice on this type of thing. But I recommend practice your integration. That's one of those things where we did it, And we had practice, but you can always practice your integration more. And then check it using your calculator. So we have 3 pi over 10, which is 0.9425 or so. So that's revolving around the x-axis. The y-axis is going to be the same, except we're going to have x squared minus x squared dy. So if we have our shape, we have y equals root x, we have y equals x. We're revolving around the y-axis, which means our big radius here is going to go out to the blue line, and the small radius is going to go to the red line. Notice if we were revolving this around the x-axis, that would change. The red one would be bigger than the blue one, but around the y-axis, the blue one's bigger than the red one, which means we're going to have pi times the antiderivative of something. We'll figure that out in a second. The blue one squared. So these are x values, so we'll have x squared minus y squared, or x squared again, just the red one. And then dy, being that this is y, we're going this way. Where do they intersect? Root x and x, they're going to intersect at 0 and 1. And now we need to solve for x. We can plug in the x's. So for the blue one, well, y equals x. That's already solved for. We don't need to worry about that. For the red one, we have y equals root x, which means we can square both sides. X equals y squared. And so we can substitute that in. X equals y squared squared. The other one being that it's just x equals y, it's just y squared. It's kind of boring, but every once in a while you get those ones that are kind of boring. Just go with it. It'll be fine. dy from 0 to 1. Don't forget the pi. Now we can simplify. Let's simplify. The volume equals pi times 0 to 1 of y squared minus y to the 4th dy. Antiderivative gives us pi y squared. It becomes y to the 3rd. So we have 1/3 y to the 3rd minus 1/5 y to the 5th from 0 to 1. Plug in 1. We plug in 1. It's 1/3 times 1 is just 1/3. Minus 1/5 times 1 is just 1/5. 5. There's a 5. And then minus, plug in 0. We get 0 for both of them. This is 5/15 minus 3/15 is going to be 2/15. So we have 2 pi over 15. 2 times pi is about 6 divided by 15 is about 0.4189. So again, notice this one was pretty much the same as the last one, except we had x squared dy instead of y squared dx. Same topic as with disks, except we have the 2 subtracting on the inside. And so that's the thing. Like if I were to sum up this topic, it would be the big one squared minus the little one squared. That's what you do. There is more to this topic because so far we've been revolving around axes. That's not the only kind of line we could revolve around. We could revolve around any line, technically. We could revolve around the line y equals x. We're not going to. Not in this class. We're going to stick to vertical and horizontal lines. So the next one, which is revolving around a horizontal line, we can look to see what that is. Now, the y-axis is a horizontal line. Y equals a number is a horizontal line. So it's going to be very similar to when we revolve around the y-axis. So if we have this equation, and notice f of x equals 9 minus x squared, and we're going to revolve it around the line y equals 15 instead of the x-axis. We're going to get a shape, looks kind of like that. In this case, the outer radius, the big one, we start where we revolve and we go down. So it's from 15 down to our function, our y value. So this radius isn't y. Y is this distance underneath. Where did my line go? Y is that distance underneath. It's what's left to get to 15. So that radius is going to be 15 minus y. So that's the big radius is 15 minus y, which we'll have to square. The smaller radius is just this. It's from 15 to the line y equals 12. It's not specified right here in the equation, but it's the line y equals 12. The distance from 15 to 12 is 3. It's always 3. We get that, though, because it's 15 minus 12 squared. It's not variable. It's just a constant. It could be variable. It could be 15 minus 1y squared minus 15 minus another y squared. It's done the same, except this will be a little bit easier because one of our things will be a number. And as we're doing this, notice the big radius, it's not the top equation right here. The big radius is the bigger distance to the axis of rotation. So if we were rotating around the x-axis, instead of the line y equals 15, these two things would be switched. Now, if you do accidentally switch them, what's going to happen is your answer is going to be negative. It's going to be the same number, only with negative. So if you do one of these problems and you get a negative answer, the very first thing I would do is check your equation. Did you switch it? Relook at the graph. If that's the case, great, you probably just found your mistake. If that's not the case and you had them right, it means your mistake was elsewhere and you'd have to find that differently. So we have from 15 to y squared minus 15 to 12 squared. We're going to take the antiderivative, pi, volume, a dx over here because we're doing it horizontally, the width of our washers, just like if these were discs, the width of the discs would be dx. And then our y values, or x values, we're going from 0 to 3, which it mentions in the problem. I just didn't mention that. So we're going from 0 to 3. And in this case, it would actually tell us from 0 to 3. So let's simplify this. Volume equals pi, 0 to 3, 15 minus y squared. We're going to want to square that out. I know, you just groaned. You can do this. It's just a polynomial. And remember, this is not 15 squared minus y squared. Don't be that guy. This is 15 squared is 225. And then there would be a minus 15y, another minus 15y, so we'll have minus 30y plus y squared. And then minus, this is just 3 squared, so it'll just be minus 9 dx. We can simplify. We have the 225 minus 9. So we have from 0 to 3, 225 minus 9 is 216 minus 30y plus y squared dx. Totally forgot to substitute y in. That's okay. We could actually still substitute y in right here. Y is 9 minus x squared. Oh, that's going to be more obnoxious. We're going to erase that little bit. Slide. Yeah. We're going to just go erase. It's not just a dotted line maker. It does other things too. All right. Try this again. First, let's substitute in the y. 0 to 3. 15 minus y. Y is 9 minus x squared. So we have 15 minus 9 minus x squared. Then that'll be squared minus 3 squared dx. 15 minus 9 is going to be 6. I thought the numbers were getting just a little bit too big. So we'll have a 6 plus x squared minus 9 dx. Now we can multiply that out. There we go. Volume equals pi, 0 to 3. 6 squared will be 36, plus 6x squared plus 6x squared will be plus 12x squared, plus x to the 4th minus 9 dx. 36 minus 9 will combine to give us a 27. So we have volume equals pi times the antiderivative of 0 to 3 of 27 plus 12x squared plus x to the 4th dx. And now we can do the calculus step. So far this has been algebra. Technically setting up the problem was probably calculus, but all that stuff was algebra. So calculus step. The volume will equal pi times, this will be 27x. That'll be x cubed, so we can divide by the cube to get 12 divided by 3 is 4. So plus 4x cubed, and then plus 1/5 x to the 5th from 0 to 3. So we can plug in 3 to get 27 times 3 is 81 plus, that's 3 cubed is 27 times 4 is 108 plus 3 to the 5th is 243 divided by 5 is 243 fifths minus, plug in 0. God, work. And 0 is going to be 0 for all of them. So now we just have to combine our like terms so we can make each of these into fifths, which is what I would do. You could also turn the 243 fifths into a mixed number, since these two are whole numbers, and add them together. I like improper fractions, so I'm going to turn them all into fifths and combine them. So we have 81 fifths is going to be 405 plus 540 plus 243 should give us about 1,188. 1,188 pi, come on pen, over 5, which 1,188 pi over 5, if we do this calculation, we should get about 746.44 or so. 46.44. So this one, yes, it was a bit more obnoxious to do that. And these ones are really where you get into the set it up or set it up and use your calculator. But again, the practice integrating, the practice multiplying, the practice with the precision will only make you better, because that's what practice does. I love practicing this stuff. Like, it's great. I love like just doing it, thinking on my feet, and it's fantastic. And I recommend doing it by hand and then check your answer. All right, so that's about a horizontal line. Let's look at one revolved around a vertical line. So here we have our shape revolving around the vertical line, y or x equals -2. And so in the last example, the line was over here. It was bigger than our axis. This one, it's smaller. That could be reversed. We could have this one over here, just like we could have the other one underneath it. That's fine. In this case, our radius, we have an x value, so this is x, but we have an extra 2 to get out there. So our radius, the bigger radius, is going to be x plus 2. So we're going to have an x plus 2 squared minus, in this case, our line, it's again a straight line, so the inside's going to be a perfect cylinder instead of something kind of weird. That's okay. That's what they're going to be most of the time that you're going to see them. But it could be another thing. We could have the line y equals x there. It can happen. It's fine. But the inside is just going to be this distance, which is just 2. So we'll have minus 2 squared, just like last time we had minus 3 squared. Going to have pi times the integral from something to something dy. So where do these hit? It's going from 0 to 9, because when x equals 0, y equals 9 minus x squared equals 9. So we'll go from 0 to 9. And that's going to be our volume, equals that. Now we're going to substitute in for y. So we have y equals 9 minus x squared. We could change that to x squared equals 9 minus y, which we don't have an x squared, we have an x. So we do have to square root. X equals the square root of 9 minus y. Now, I know when you square root both sides, you get plus or minus, but in this case, we're only looking at the positive side of it. We don't need the negative side of it. Is it possible we could only be looking at the negative side of it? Yes, it is possible. Not very likely. I've seen it once or twice, but kind of in obscure places. That is possible, though. But in this case, positive side, so we'll just focus on that. Substitute that in for x. So we're going to have the square root of 9 minus y plus 2 squared minus 4 dy from 0 to 9 pi volume equals. Multiply it out. So when we multiply this out, we're going to have the square root minus or times the square root will just be the inside. 9 minus y plus 2 times the square root plus 2 times the square root will be 4 times the square root of 9 minus y plus 4 minus 4, because that guy, notice this plus 4 minus 4, that happens a lot with this type of problem. Dy. Now we can do the antiderivative. Volume equals pi times the antiderivative of 9 is going to be 9y minus 1/2 y squared plus that one we're going to need some u substitution. So I'm going to come up top here. I'll switch to green. We have 4 root 9 minus y dy. We could have u equal 9 minus y, which means du equals negative dy. Well, we have dy, so let's move that over there. So this will be 4 times the antiderivative of, come on, pen, right, u du, and then we need the negative. That's u to the 1/2, which becomes u to the 3/2. Flip it, so that'll be times 2/3. So that'll be negative 8/3 u to the 3/2. Plug u back in, and we get minus 8/3 times 9 minus y. Come on. 9 minus y to the 3/2. From 0 to 9. All right. So now we can have my pen work consistently. Pi, plug in 9. It's going to get us 81 minus 9 squared is 81 times 1/2 is 81 over 2. Minus, when we plug in 9 here, 9 minus 9 is 0 to the 3/2 times something is just minus 0. That's okay, but be thinking when we plug in 0, it's probably not going to be 0. So now plug in 0, so minus, plug in 0 to 9y, that's 0, plus plug in 0 to the 1/2 y squared is 0. And then plus, because it's minus the whole thing, so that negative distributes, we'll end up with plus, plug in 0. We have 9 to the 3/2 is 27. How did I do that? I would do the half first. That's a square root to get 3, and then cube it to get 27 times 8/3. 27 divided by 3 is back to 9, times 8 is 72. So we're going to have 81 minus 81 over 2 plus 72, all times pi. We can make common denominators of 2 if we want. And so we'd have 162 minus 81 plus 144 will give us a volume of 225 pi over 2, which is about equal to 353.43. So, again, this one, there's a lot going on because we were solving it by hand. The new stuff, and a lot of times the important thing here, is going to be, can you write it out? This step, and then a lot of times it would go from here to plug in to the calculator to get your answer. Again, I recommend doing them by hand. It is fantastic practice. When it comes time to for a test, especially a big test like the AP test, if this is a calculator problem, I would go from there to there because there's lots of places to make mistakes in the middle, and it's a time-sensitive test. You don't want to be bogged down with these computations if you don't have to. That will be tested elsewhere. So use the tools smartly, but don't give up knowing the topic because you're using the tools. And so we have revolutions around vertical and horizontal lines, as well as revolutions around the x-axis and y-axis, all with washers. It's just radius squared minus radius squared, find the antiderivative, and that's it. So this topic. It's the last big topic of the chapter. The next topic is actually a small topic, unless you're BC. Then we have another one after that. But until next time, keep working problems, keep asking questions, and as always, happy mathing.